Okay, so here's the video for section 9.5 symmetry. Um, it's mostly definitions and kind of generalities in it, but there are a couple of spots that do have some real specific things that go on. So especially at the end, there might be a couple of definitions that might be kind of confusing. So hopefully this is a straightforward section though. We've drawn reflections, rotations. Now we're going to talk about line rotational symmetries in two-dimensional figures. And then the part that's probably going to be confusing if anything really is, it's the three-dimensional line and rotational symmetries. Those are kind of harder to see. Yeah, mostly because we don't have a lot of experience with it. Next, so first definition, symmetry in two-dimensional figures. A figure has symmetry, okay, if there exists a rigid motion, a reflection, a translation, a rotation, or glide reflection that maps the figure back onto itself. So the first type is line symmetry. So this is the one we're probably most familiar with calling symmetry. That's the reflection symmetry or line symmetry. Basically, you can draw a line through it and it reflects the image on both sides of it. So if we were to reflect across this line, we get the exact same drawing. That's basically what it means. So again, definition-wise, a figure in a plane has line symmetry or reflection symmetry if the figure can be mapped onto itself by a reflection in a line called a line of symmetry or the axis of symmetry. Okay. So here's our first example for that. Kaleidoscopes. I guess they're trying to give you a real-life application because all of you guys care about kaleidoscopes. So they want us to say whether the object appears to have line symmetry. Yes or no, and if so, draw all the lines of symmetry and then state their numbers. Okay, so it's going to probably come out a little better on the screen here. It may be on your worksheet, hopefully, than it does on mine. But I have the drawing of it here. Oops, wrong button. So here we go. This is our figure of a kaleidoscope drawing. Try to see if I can get a little bit better light on it. Yeah. So we have to figure out, does it have symmetry or not? Well, basically, what we're trying to think of is like if I folded it over on itself, would it look the same? And then if so, where are those things happening at? So if you look, the key is there are these little kind of things that hang out, like arrows almost, and then across from them there are like these almost like diamond-shaped figures. And every time there's one of those little lines, doesn't matter where it's at, little arrows in here, there's a line that goes through it. That's another line we can draw. So there is line symmetry. So let's see how many we can draw here. Draw one. And a lot of times what I do is I turn the paper then. And there's another arrow, so that's two. There's another one, three. Another one there with the arrow, four. Five. Six. And seven. Now I know it's seven because I counted out as I went around. And the next time I come around, I come back to myself again. You can also figure it out by this. Count the number of times of these guys you have and then divide it by 2, because what you're doing is you're like, if I count this one and then count this one, I'm double counting the same line. So if you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But take 14 divided by 2, there are 7 lines. So yes, 7 lines. Okay, and I got another one here that I didn't put on your worksheet, but just to show you that not all of these will have line symmetry even if it's round. Hopefully it's kind of obvious by looking at this big screen here that none of this is going to work, because if I try to fold it upon itself, all I end up seeing is I don't see the exact same figure, mostly because there's a triangle here, there's a circle here, they're not across each other. There's a weird blue circle here, but this is like a red or a green circle here. So this one has no line symmetry whatsoever, so our answer for this one would simply be then none, or no. Okay. Rotational symmetry. Okay. Rotational symmetry is a symmetry where the question is, if you rotate it about a point, like a center, they call it the center symmetry, can you get the same figure again? So a figure in the plane has rotational symmetry, or we call radial symmetry, if the figure can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure called the center of symmetry or the point of symmetry. The figure below has rotational symmetry because at a rotation of 90 degrees, okay, so it starts here at 0. If you only go 45, it doesn't look the same again. But if you go 90 degrees counterclockwise, it does look the same again. Same thing as if you go 180 or 270. So we say it has rotational symmetry because if you rotate it 90 degrees, 180 degrees, or 270 degrees, it maps on back to itself. Now you might say, what about 360? We don't count 360 or 0 because the 360 is a whole rotation, so it doesn't really count for us. Same thing with 0, it didn't move at all. So both of those things, yes, we give you the same figure if you rotated 0 degrees or if you rotated 360 degrees, but they're not important for us because every figure should have that kind of rotational symmetry. Now there is a little formula for this, okay, and this is something else we have to do. It's called order, and the order of symmetry tells you what angle you need. In fact, if I go back to the drawing here, I knew it was 90 degrees. That is called the magnitude, which is the angle of rotation. That's the smallest angle that would give us the same figure. So we have an order, which is how many times does it repeat itself, and then we have magnitude, which is what angle makes it repeat itself, and the smallest angle specifically. And so for the figure before, we had it happening at 0 degrees, at 90 degrees, at 180, and at 270. So it's the same thing 1, 2, 3, 4 times, because 360 sends it back to the original figure. Now, to figure out the magnitude, then all you do is you take 360 degrees, which is one full rotation, and you divide it by the number of times it looks like itself. Okay, and so that's how we find our magnitude in order. So here we go. We have this star here. So in a second, I'll ask you what's the, it does have rotational symmetry. I'm just going to say that right off the bat. It does have it. The question is, what's the order? What's the magnitude? Okay, so we'll take a look here at the drawing I've got of the star. Okay. Now the easiest way to do this, at least in my opinion, is to pick a point that's easily referenceable. Like for instance, this is a star. Pick at the end of a point. And then I make a dot basically. And what I do is I turn it every single time until it looks the exact same as it was before, and then put the dot right there. So the point was standing straight up, there's a point. Does it happen again? Yeah, standing straight up there. Does it happen again? Yeah, standing straight up right there. Does it happen again? Yep, standing straight up right there. And then once I get back to that original dot, I stop. Okay. And basically now I've figured out how many times this guy repeats himself. Now I know you might say, well, it only happened 4 times. This one here is the beginning. Yes, we still count that as one of our times. So it happened 1, 2, 3, 4, 5 times. That is the order. Okay. Order of symmetry is 5. Okay. Now, if it happens 5 times over one full rotation around, that's what we take that 360 at for the magnitude. Over the course of 360 degrees, it was the same figure 5 times. That ends up giving for us then 72 degrees is our magnitude. And that means that's the smallest angle I have to rotate it. So if the center is right here, which is really what the center of location is, or center of symmetry, right here, and it goes out to the next turn, this guy here is 72 degrees. Okay, so that's the magnitude. So all I have to do is turn it 72 degrees, and boom, I'm back to the same figure. Okay. All right, now the last 2 types of symmetry are the 3-dimensional symmetries, and these are probably the most difficult to sort out. It's partially ability to just see the figure in your mind and turn it in your own head, or if you could, kind of turn the paper and kind of just look at it in a way to tell. So the first is plane symmetry. So plane symmetry is just the 3-dimensional way to say line symmetry. Can you cut a line through it that gives you the same thing on both sides? That's 2 dimensions. In 3 dimensions, we can't cut it with a line, really, we cut it with a plane. And so a 3-dimensional figure has plane symmetry if the figure can be mapped onto itself by a reflection in the plane. Essentially, the bigger thing is, can a plane cut it in half, like perfectly in half? If it can, it has plane symmetry. Axis symmetry is the way we have line symmetry for 3 dimensions. So instead of reflecting across a line, basically what axis symmetry means is you could map the figure on itself by rotation between 0 and 360 degrees in a line. More importantly, what you got to think about is, is there a line that I could rotate it about that would give me the same figure again? Okay, we don't care about the degree as much as just does it have it, because it's hard to see sometimes. So here's the first problem. We're looking at this kind of weird, I don't know, L-shaped box. The question is, does this have plane symmetry, axis symmetry, both, or neither? Okay, so looking at this guy, not having it in 3 dimensions is kind of tough to tell. But the way to think about this is if I turn it this way horizontally, it never looks the exact same again until I get it back to itself. So it can have rotational. And if I turn the paper and think about this, like, think about an L shape, if you turn it, this guy here is at top, then he's out, then he's bottom, then he's back out that way on the other side over here somewhere. It never happens until it gets back to itself again. So there is no axis symmetry. There's no rotational line symmetry. There is, however, a plane symmetry. You can cut it in half by cutting, a vertical line through it. And I apologize, my drawings are always horrific. Okay, so if you think about that, I could cut it along that plane inside, and it would have the same thing on both sides of it in the middle. So it does have plane symmetry. Okay. And again, that's kind of tough to see. You have to be able to do a little visualization and kind of, again, rotate or cut it in your head. Okay, next example then, a cone. And the question is, does this have plane symmetry, axis symmetry, both, or neither? Okay, so looking at this one, it doesn't matter where you start at if you try to think for plane or try to think of axis symmetry. If you think about a cone, any kind of cone at all, it does have plane symmetry because you can cut it right down the middle. I know you can't really see it. I'm trying to cut it 3-dimensionally, but you can cut it right down the middle and think about it cutting that way, and what happens is you've got half the cone over here and half the cone over here if you kind of cut it that way. Okay. So it does have plane symmetry. Plus, any cone, and I'll just redraw the cone because I've already kind of messed it up as it is. Any cone also has axis symmetry, because if you draw a line that goes through the vertex of the top and then goes to the middle of the cone, and you think about turning it, the cone always looks the exact same. So it also has axis symmetry. Okay. So a cone, no matter how you turn it, or no matter how you orient it, peeking upwards, or like this one, peeking downwards, you're always going to have both plane and axis symmetry. Okay, so that's section 9.5. We'll go through questions in class, and again, I expect we'll have a lot of questions probably with the plane and axis symmetry.